chemistry, they told you something about electrons. An electron is part of an atom. It's a very small part of an atom. If you look at an atom, the atom consists of protons and neutrons that weigh 10 to the negative 27 kilograms, and an electron is 10 to the minus 30 kilograms, or roughly. So, like 3 orders of magnitude difference in the mass. And the atomic number is equal to the number of protons in the nucleus of an atom, and also the number of electrons in the neutral species. And we're going to discuss what neutral species actually means. Atomic mass unit, by convention, is 1/12 of the carbon mass. Now, does anybody know what an Avogadro number means? Yes? Number of moles in an atom. Actually, it's the number of atoms in a mole of matter. Okay? And a mole is another measurement. So that is equal to 6 when 0 to 2 times 10 to the 23 molecules or atoms. So the atomic mass of carbon is 12.011, hydrogen is 1.008, and so on and so forth. So this atoms is what everything consists of. We're made of those atoms. Okay? Atomic structure determines many different properties, and specifically the electronic structure, or atom's electronic structure, controls how they're going to behave chemically. They're going to be determining electrical properties, also thermal properties, and optical properties. And these are the properties that we're concerned with, right? Because the idea is to control the process, to control the structure, to control the properties. And we're going to talk, each one of them is, except for chemical, is a chapter in this course. So you might have heard in your chemistry class that electrons have dual character. Sometimes they're acting as waves, and sometimes they're acting as particles. That's why there's mass associated with them. So 2 wave-like characteristics are electron position in terms of probability density, because we cannot really know the physical position of an atom at every point in time. So we cannot write the equation of motion. Okay? This is the paradigm of the quantum mechanics. We all agree that we're presently here in this room, correct? Is anybody not here? I mean, it can happen if maybe in alternative states of mind, but I mean, or maybe you're dreaming, right? You're dreaming that you're in the class. So pinch yourself and make sure that you're not dreaming. But from this perspective of an electron can be somewhere else. And that somewhere else is maybe not even in this world, if they exist. So this is the problem with quantum mechanics, which is still being developed. But the other thing is that the shape, size, orientation, and probability density is determined by the quantum numbers. So let's review what quantum numbers are. N is the principle that determines the shell, and the values are K, L, M, N, O, so on and so forth. And then there's a number, a Roman number, or Arabic number, 1, 2, 3, 4, and so on and so forth. Then the subshell is denoted by the letter L, which is the azimuthal, and those can be S, P, D, or F, and they start from 0 and they go up to n minus 1, where n is the principal quantum number. And the reason they're called orbitals is because this is the path of an electron, and if we look longer enough, there's going to be a certain shape of the trace. Like if I take this LED light that works and then at night I start to rotate it, then you're going to see a circle, this kind of thing, right? Or if I do an 8, you're going to see an 8. If I do it fast enough. Then there's a Amsabel, which is a magnetic. That's not related to the orbitals, and it's 1, 3, 5, 7, or it varies from minus L to plus L. And then there's a spin of 1/2 and minus 1/2. Does this ring a bell? They told you this in chemistry. Maybe you didn't quite know why. Electron energy states is, the term is quantized. And what it physically means, and I can try to explain to you relatively easy. You see this rows and the seats, and you can occupy any seat possible, and so can I. But there's nothing in between, okay? There are no people standing in between. And there are no people sitting between the chairs. That is what we mean by quantized energy states. And in terms of the energy, we start with 1s, which is a K shell, n equal to 1. Then we go to 2s, 2p, 3s, 3p, 4s, 3d, 4p, 4d, and so on and so forth. And I'm sure you spent quite a bit of time writing down the electronic configuration of the atoms in your chemistry course. Just like this. So hydrogen has an atomic number of 1 and its electronic configuration 1s1. How electrons can be on the s shell? The maximum number. 2. So hydrogen is missing 1 electron. Just remember that. Helium is an inert gas. And helium has 1s2 configuration, and it is stable. Why is it stable? And why is it called inert gas? Because its shell is filled, and electrons participate in the processes that we are going to discuss today. Lithium, 1s2, 2s1. Beryllium, 1s2, 2s2, and so on and so forth. Neon, 1s2, 2s2, 2p6. On the p shell, there can be 6 electrons, and it is stable. The rest of them are either missing electrons, they are all missing electrons, or those electrons can be excess that can participate in certain processes that we are going to discuss. Krypton, not kryptonite, but krypton has a configuration like this. Why these guys are not stable, where it doesn't say stable? And what is meant by that? Right, the outer shells are not filled. And that means that there are some empty seats. And then think of it this way. It means that those seats can be either occupied, or these atoms can provide their electrons to other atoms for purposes of bonding. Okay, so what we define by valence electrons are those in the outer and filled shells, and filled shells are more stable, meaning that they require more energy to gain or lose electrons. Right? Why is that? Because you can see there's certain energy associated with transferring an electron from one shell to the other, which is also possible. Right? They told you this in chemistry. And this valence electrons, they participate in the bonding. So if we look at the carbon atom, for example, atomic number is 6. The configuration 1s2, 2s2, 2p2. And even though the 2s is filled, it still participates in the valence in the bonding process as well. So these are 2s2 and 2p2 or valence electrons. Iron, which has the atomic number of 26, is 1s. K shell is filled, 2s is filled, 2p is filled, 3s, 3p, 4s, 4d is not, and then we have the 4p and 4d. So the electronic structure is 3d6, 4s2, and these are the valence electrons for the iron. A periodic table. The guy who put it in a periodic table is a genius. You know the name by any chance? Who invented the periodic table? Nobody knows. It's okay. Mendeleev was the guy. He also invented vodka. And he did a lot of experiments with that. The story is that it came to him in a dream. And what he decided to do is he decided to arrange all of the atoms in a table. And that's why the table bears his name. It's called Mendeleev periodic table. Now, there's a property that's called electronegativity. And elements in each column, they have very similar electronic structure in terms of the valence electron. And obviously, as you go from top down, they become heavier. This is the atomic number that's written in the periodic table, so they're all numbered. And it starts with a hydrogen. And hydrogen is the smallest atom that's missing one electron, and it's one and only S shell. So hydrogen is very reactive, and it is small. Okay? So I wish I drove a hydrogen car today. With AI or without AI, doesn't matter. But there's a reason why I'm not driving a hydrogen car to work today, which is fuel density. Any other options or ideas? Have you heard about a hydrogen bomb? Not enough fuel density? What are you talking about? There's a lot of energy there, but when you burn hydrogen, what is the product? Water. Is water causing any pollution? Is there enough oxygen in the air to oxidize hydrogen? Have you ever played with hydrogen? Don't do it at home. Why? Because hydrogen is extremely flammable. So it burns. The problem with hydrogen, or one of the problems with hydrogen, is the size. Okay? It's very small. So it's hard to store it. We can generate hydrogen, it's not a problem. It's the problem of storing it. And then about the energy density, if something happens and it gets ignited, I mean, somebody gets in the car accident and they're driving a gasoline car, what do you do, or what anybody should do after a car accident? Huh? Get out of the car. Why? And if fuel leaks, then what? Then what can happen? It can burn, blow up. I mean, you need to have a lot of gas for it to blow up, right? But with hydrogen, you're not going to have enough time. It's another reason. So maybe the future technology, the way I personally see it, is generation of hydrogen on demand. Like, you can, there's a process called electrolysis. If you put two electrodes in water, you're going to have separation of oxygen and hydrogen in that water. So you're going to generate hydrogen-containing gas, which may help you burn the fuel a little better. You know, maybe that's the future. But for now, since we're on this subject, do you know Elon Musk? Okay. When the rocket, when do they have a new launch coming up, right? Have you ever seen a launch? Not in person? Are you interested in this kind of stuff? Okay. What is the main difference, again, philosophically, between what happens on the planet Earth versus when you get into space? Gravity, air pressure,
velocity.
Velocity in terms of like what? Time. You can have a lighter, right? And you can light a lighter or a match. Match is made from what? What a match is made from? Wood or maybe paper, right? And what happens when it burns? Lights up. Is there a chemical reaction? With what? Oxygen. Is there oxygen in space? Okay. Huh? You have to bring your own. It doesn't have to be oxygen. It has to be some species to oxidize, or oxidize, maybe you're not going to be oxidizing, right? But you're going to be having another substance to react with your fuel, right? So the fuel up there has to have at least two components. Does that make any sense? Okay. Also, you see that most of the materials or elements in the periodic table are metals. So in the group 1A, they can give up one electron. In the group 7A, they can accept one electron. So there's a big driving force for these guys to react. So electropositive elements are giving electrons to become positively charged ions, and the electronegative elements are ready to acquire electrons, so they become negatively charged. And electronegativity, which ranges from 0.7 to 4, you can see that on the left side there's smaller electronegativity. On the right side there's larger electronegativity. And I'm going to throw this in because the slides are not made by me. But I do have a question for you. What is the physical meaning of 3.0 and 2.0 and 1.0? Why is there an O? Does anybody know? I mean, mathematically, it's meaningless. If you have $1 in your pocket, you can add as many zeros to that dollar. It's not going to become 100. I wish it was. Some people say that it shows precision, meaning if that it's 2.0, like there's 2.1 and 2.5, and this 2.0 means that there can be another digit. But please be cautious, because I've seen examples where there are 8 zeros. And at that point, It just has no physical sense. So when you buy gas at a gas station and it's $3.19.9, how much you're actually paying for the gas? $3.20? Well, what if you buy 10 gallons? Yeah, so you'll be saving one penny. Have you thought about that? The reason I tell you this is this happens a lot with the students. Like, what is meaningful and what is not meaningful? Like, we're going to be dealing with very large numbers and very small numbers. Is 6.22 in Avogadro's number, 6.022, is that meaningful or not? Why is that meaningful? Because there's a whole bunch, how many? 23 more zeros. Okay, and that's meaningful. Okay, so that's my point. It's just, when you're dealing with large numbers, when you're dealing with small numbers, you don't have to be as precise as you want to be. And if you're too precise, and I have examples, for example, if you're measuring temperature and it's 1,000 degrees centigrade, and somebody gives you a number 1,000.001 degrees, what does that mean? 1,000ths of a degree at 1,000, do you think you have the resolution and the accuracy to measure 1,000ths of a degree at 1,000 degrees? What do you think? Probably not. But how do you know where you're supposed to put or where you should be rounding or not? I guess it comes with practice. Okay, let's go back to this electronegativity. We talked about ionization. And what is the definition of an ion? And why? And why? Okay, this iron here, what is the charge? Is it charged? Or is it neutral? Iron has no charge. But if an element is losing electrons or accepting electrons, it attains a charge. And the charge can be either positive or negative. And one is called anion, and the other one is called cation. And which one is positive? The cat is positive? Okay, good. How do you remember that? Because I always mix them. Because the cat is positive? All right, there you go. I'll remember it from now. The cations are positively charged. The anions are negatively charged. Well, what does that mean? I have a little piece of paper here. And I don't know if that's going to work, but I'm going to try. And it depends, like, on the humidity level. What am I doing now?
Static electricity?
Okay, let's see. Did you see that? You can do this at home. No harm. Okay, what did just happen? Forces of nature. What kind? What did I do by going like this? Or actually, you know what, maybe this is better because this is wool. Let me try this. No, not as good. Not as good. Much better. So what I just demonstrated is called static electricity. This thing weighs quite a bit. If you think that piece of paper doesn't weigh that much, it weighs a lot. Right? And what did I do? I transferred electrons, whatever way, right? And I just did an experiment for you. So, let's say we have a metal atom. And typically metals have excess electrons. So if it donates electrons to the nonmetal, then the nonmetal is going to accept those electrons. Like example is magnesium oxide. Magnesium has 2s2, even though they're filled, and the oxygen is 2p4. How many electrons can be on the 2p shell maximum? 6, right? The p shell looks like this, kind of like this, but in 3D, right? And then, here's the configuration of Mg2 plus, and this is O2 minus. And then after this electron transfer, once this became a cation and this became an anion, they start to interact through Coulombic interaction, just like what I just demonstrated to you now. And that is ionic bonding. So ionic bonding happens between positive and negative ions. Well, ions by definition are either positive or negative, but there has to be opposite. Have you heard opposites attract? Pluses and minuses attract. It requires a transfer of electrons. And for that to happen, there has to be a large difference in electronegativity. And the good example is table salt, sodium chloride. So sodium gives an electron to chlorine, and then they are interacting through Coulombic interactions. If we look in terms of the energy, here's potential energy, and here we have attraction versus repulsion. It is described what is called scientifically a Lennard-Jones potential. The total energy consists of the attractive and repulsive parts. Okay, and this is the repulsive part, meaning that if we bring those ions closer, they would start to repel each other. If we pull on them, they would start to attract each other. Okay, and this is the net curve, which is a sum of the attractive part and the repulsive part. R is the distance between those atoms. So you can see that the attractive part goes as 1 over R, and the repulsive part goes as R to the nth power. There'll be another example where the two curves are going to be applied in terms of the internal energy when we talk about Gibbs free energy. So this is an example where the two terms get added. They're actually two functions, right? And we're only considering two individual atoms. So this determines a couple of things. It determines this E0. It's called the depth of the well. It also determines R0, which is the equilibrium position. And what is the physical meaning of a derivative of a function? What does a derivative mean? Change, rate of change. So like if I were to draw a derivative function of this, the physical meaning would be the slope at every point. I can calculate. I'm going to keep coming down and keep changing the slope. And over here, what is the slope? 0. This is why, like mathematically, you learned this in which course? That if you take a derivative of a function and you set it to 0, that allows you to find the minimum and the maximum of a function, right? So for this equation, we need to differentiate it and set it to 0 to find this point, which is going to determine the equilibrium interatomic spacing. Okay, ionic bonding is predominant bonding in ceramics. Here are some examples. These are on the opposite sides of the periodic table. These guys on the left give up electrons. These guys on the right accept electrons or acquire electrons. Any questions about ionic bonding? Please also realize and appreciate that this ion is going to have a certain dimension, which we're going to approximate as a ball later on, a sphere. Okay. Another type of bonding is covalent bonding. And the difference is when they have similar negativities, and as a result, they are sharing electrons. For example, the hydrogen molecule or hydrogen gas, they share one electron. Each one provides one electron, so that at least part of the time, those shells are filled. This is the radius of an atom. And the fact that they are sharing means that their orbitals become to overlap a little bit, which does not happen in ionic bonding. So in ionic bonding, those shells are not touching, but close to be touching. For covalent bonding, those shells overlap, so that the distance between those atoms becomes smaller. And in fact, covalent bonding is the strongest type of bonding. And true covalent bonding only happens like in the same element, like hydrogen. 100% true covalent bonding. I used to make an analogy of a pizza. I don't know if that's a good analogy, like if we were to get pizza for everybody in the class. Somebody has more money than the others, cash. So I'm not going to make this analogy, but you can come up with your own analogy as far as what happens when this bonding happens. There's what's called hybridization, and carbon can form what's called sp3 hybridization. So these are sp3 orbitals, and the electronic structure from 1s to sp3, that's why it's called sp3 hybridization, because there's a certain angle associated with that of 109.5 degrees. And carbon forms this hybrid orbitals. They're hybrid because electrons are being shared in those orbitals. So what is the shape again of the s orbital? A sphere. And the p? We used to draw them like almost like an 8, but it's in 3 dimensions. So that's relatively the shape of a p orbital. So here's an example of methane gas, CH4. Carbon has 4 valence electrons, and it needs 4 more to finish this. And hydrogen, it has 1 electron, so it needs 1 more. So what you can do is you can add hydrogen into each one of those. And that's why it's CH4, because the electronegativities of carbon and hydrogen are similar, and the electrons are shared in sp3 hybrid covalent bonds. Here's an example. And this is the region of the overlap. Any questions? Please remember that covalent bonding is the strongest type of bonding. And if you ever decide to get a master's degree or an advanced degree, you need committee members that are going to be helping you with your thesis. True story. A student that I've never seen in person before said, "Can you be on my committee?" I said, "Yes." And they put their thesis in my mailbox. They never came to visit me. And I always had this question in my head if professors are actually reading any of that stuff. So when I was a PhD student, you know what I did when I wrote the dossier? I gave it to the committee members and I glued 2 random pages. And I gave it to the 3 committee members. I didn't do it for the thesis, but I did it for the dossier, which is like pre-defense. And you know what the result was? At the University of Minnesota, they at least looked through all of the pages because those pages came back separated. I didn't tell this to nobody. Of course, I didn't tell it to the professors, but anyway. So this person goes for the defense, and then there's thesis. They write that covalent bonding is the weakest type of bonding, which is completely the opposite. And it's a simple mistake that's very easy to correct. It's for humans. It's very easy to flip a plus and a minus. I mean, it happens all the time because I guess that's how we're wired. But we had a discussion about bonding during the defense. My point is that if you give something to read through faculty, they're going to read it most likely, and please make sure that you get the feedback before you come out for like an important event like a defense. And remember that covalent bonding is the strongest, true covalent bonding is the strongest type of bonding. The next type of bonding is metallic. And the electrons in metals are delocalized. What does that mean? It means that they do not belong to any particular atom. And they form what we call electron cloud. So question to you, if you know, what is the mean free path of an electron in a metal when you apply a potential? You apply electric field that causes the electrons to move. By the way, the electrons are charged with how they charged. What's the charge of an electron? Okay, so when you apply bias or when you apply voltage, where are they going to go? Yeah. And I do have another question for you because it's related to the class and it's something to incident. Okay, something happened.
What?
How many of you change your own battery in the car if you have to? Okay. How much was your battery last time you changed? 300. What car do you have? Okay. Where's the battery located physically? In the trunk, so it's inside the car. Okay. The reason his battery and my battery is $300, or one of them, is because the battery is not under the hood where the acid can vent, but it's inside the actual compartment. So potentially you can breathe the fumes. And my daughter's friend, when I was abroad, left the light on in the car, and the battery died. So then something that would take me like 5 minutes to change turned to a big ordeal. I said, okay, You can pay somebody to replace your battery. She's like, it's not my car. I'm not spending any money. I'm like, okay, then you're not going to have a car. Or I can arrange for you to participate in the process, because my friend is going to help you, but he's not going to change it. You have to learn from this experience. In the end, it actually worked. But why was I telling you this? I tell you why. On your battery, there are two electrodes, right? And one is a plus and another one is a minus, correct?
There's the S.
The plus goes to the battery. And where does the minus go?
Into the frame.
Negative. Where does negative go from the battery?
Into the frame and into the ground.
Into the frame and into the ground. You know how much saving it is? Because in the car you only need one wire. Because the rest of it is the car itself. Have you ever thought about it? What if now your car is not made from metal? True story. When I was a graduate student, I was flying an international flight. And it was a Boeing plane. And there was a VCR. Everybody knows what a VCR is? Like nowadays, you have your own personalized television, whatever, right? Back in the day, there was one VCR, so everybody watched the same movie. And the VCR got stuck. In other words, the stewardess was pressing the buttons and he was not reacting. You know what they decided to do? They decided to power down the plane to reset the VCR. And I'm in there, I'm like, this doesn't sound like a very good idea to power down the plane. Why? Because the VCR is plugged in. There's no on-off switch. There's no. So I said, just wait a minute. If you agree, I can reach in the back, and there's a fuse. If I unscrew that fuse, that would reset it. They actually let me do it, believe it or not, like 30 years ago, and it worked. The problem with a composite plane, you know what's the main problem is? There is no ground. There is ground, but there's a separate wire. And you know how many wires are in the plane? Just like for the same reason this LED failed within a couple of months, a lot of things can go if you double the number of wires. Anyway, why was I telling you all this? Yes, the mean free path of an electron in a metal is how long? Please fact check me. Ask Google or somebody, what is the mean free path of an electron in a metal? And I can tell you that in this day and age, I can't bullshit. I did in the past. And another good example would be the 12th century glass that we're going to talk about in Europe for the crystalline states. Please remind me of that. What is the mean free path of an electron? Yes.
The average distance the particle travels with the light.
Yes. In a metal.
Yeah. Oh,
In a metal. Yes.
4 times 10 to the negative 8 meters.
4 times 10 to the negative 8 meters. So 40 nanometers. Nah, that's still low. That's for copper? No way. Silver at room temperature. 53 what? Is that right?
It says even though 40 times small, it's actually 100 times larger than the distance between individual atoms and the metal atoms.
Okay, put in the word average. Okay. Anyway, it's big. Like you said, it doesn't sound like a lot, but it is big. Now, ask if, is there any metal that has 1 centimeter mean free path of an electron before it collides with another electron or another atom? For the bulk. And in the meantime, I'm going to continue. If we have 2 different atoms, like A and B, by definition, they're going to have different electronegativities, right? And if they have different electronegativities, we can calculate the percentage of the ionic character versus covalent character. And that percentage is equal to 1 minus E. E is equal to what? What is E? Which is what? How much is E? 2.72. And XA and XB electronegativities of the 2 elements. So, if we, for example, take magnesium oxide, magnesium you can look up, electronegativity is 1.2, oxygen is 3.5. We calculate this value to be 73%. So it is 73% covalent, which means that the rest, 27, is ionic. I'm sorry, other way around. It's 73% ionic, and the rest is covalent. There's secondary bonding. It arises as the reason it's called secondary is because they're dipoles, and that's when their atoms have asymmetric clouds. Like in liquid hydrogen, or in HCl, or secondary bonding in polymers. So within the polymeric chain, which we're also going to discuss, inside the chain, the bonding is covalent. So the chain of a polymer itself is very strong. It's the hydrocarbon backbone. But the interaction between them is secondary. So that's called secondary bonding. Now, all of this review of chemistry, why did this matter? It matters because it determines many properties of the materials. Specifically, it determines the bond length, right? So if we take the 2 atoms, we assume they're connected by a spring. The spring can be extended or it could be compressed. The depth of the swell, E0, we call it the bond energy. That would be the amount of energy that would be required to cause those atoms to separate. They also determine the R0, the equilibrium position of the atoms. And it determines the melting temperature. So here's, this energy determines at what temperature the material is going to melt. Okay? This blue curve has smaller melting temperature. This dark curve, black curve, has larger melting temperature. The larger this E0, the higher the melting temperature. Why is melting temperature important for processing? Because if you want to cast something, you need to melt it. The higher the temperature, the more energy you're going to spend, the more
Did you finish
it will cost for the processing. What happens to most of the materials when they are heated up? they expand. And if something elongates, I do come prepared this time. See this rubber band? I apply the force, and as a result, what happened? It elongated. So the length was this, and after I applied the force, it became that. Correct? And what happened to the length? Did it increase or decrease? It increased, right? Because it was this, now it's this. Is that a plus or is that a minus? It increased, so it's a plus. Okay? What did I just do? Did I put it in tension or did I put it in compression? I put in tension. This is why tension is positive, because it's a plus. Okay. Now imagine I take this and I heat the temperature up. I increase the temperature, and it elongates. From the material's perspective, it doesn't matter if I applied the external force and elongated it, or I heated things up and it expanded. This measure, so here's the length L0 unheated, this is heated. I can take the elongation and divide it by the original length, so delta L divided by L0, and it has no units, and that is equal to alpha, which is the thermal expansion coefficient, times delta T, T2 minus T1. What are the units on the left side of the equation? We have meters divided by meters, so they cancel out. What do we have on the right side of the equation? T is measured in degrees, centigrade, Kelvin, right? If we subtract Kelvin from Kelvin, then what are we going to get? Kelvin. Okay. So what would be the units for alpha, the thermal expansion coefficient, so that the units cancel out? 1 per Kelvin, or 1 per Celsius, or 1 per degree. Okay? So that the units analysis is very important, because it's very easy to calculate and make sure that you're using the right equation. So the smaller this E0, the larger the thermal expansion coefficient. You can see that the depth of the potential well is also determining the thermal expansion properties. And remember, there are 3 classes of materials. What are those classes? Polymers, ceramics, and metals. And that is the reason why the bonding of the atoms is actually determining the class of the materials. So for ceramics, which have both ionic and covalent bonding, there's high melting temperature, there's large E, and there's small thermal expansion coefficient. For metallic bonding, there's moderate bond energy, moderate E, and moderate alpha. E is energy. And for polymers, there's very strong bonding inside the chain, but because the secondary bonding is weak, they have low melting temperature, small energy of the bond, and large thermal expansion coefficient. Are those LED bulbs making their way to the back? You do? You're all done looking at them? It's okay. What's the reason? Why did this fail? Yes? They're both bent. And the reason they're bent is because the incandescent bulb emits light all the way around. I don't know if there's a reflector, but these are bent so that the light goes towards the license plate, not the other way around. How many components does this have? You see that there are two chips here on one side. There's another chip here on the other side. See that? They're actually electronic components. And then there are LEDs on this side, and then on this side, and on this circular side, so that the light simulates a regular bulb. And even though each individual LED, a component of this, is rated for 50,000 hours, which is 10 times more than regular bulb, the system, which consists of so many components, is subject to the weakest link. There's even a show, the weakest link, right? Because the LEDs did not fail. Something else on this device failed. And for the incandescent bulb, how many pieces are there? Well, there's glass, and then there are metal contacts, which are in kind of vacuum or inert gas, and then there's a tungsten filament. So 3 components. Now, of course, it is subject to vibration because you're driving your car, it vibrates. You know, you only turn this on at night. You're not driving with your headlights on during the day unless it's automatic. If I want to place a phone call to somebody, I can just grab my phone and call. Now I can ask you to call somebody. I can ask you to ask him to call somebody. And then you're going to ask him. And eventually there's such a game called Broken Phone. Have you heard about that? Yeah, that's exactly what it is. So my point of bringing this up is that even though the LED itself is a much better technology compared to the old technology, both of them failed within a month, which is not supposed to happen. You tell me, how is it possible in our day and age for things to fail? Definitely they were not failing by design. Whoever made this, it was not their intention to have this thing failing. You know why? Because I can go return it, get my $20 back. I'm not going to do it because it has more value showing it to you in the class than returning it and getting the money. But you get my point. I don't know what lesson you can learn from this. If you have an older car, maybe stick to was there to begin with, why they still sell it. I don't think you can go to Walmart or Home Depot and you can buy regular incandescent bulb. Also, there isn't such a thing as eternal bulb. It's in the some fire station, I think, somewhere. And there's a camera, you can watch it. So there is a way to make a bulb that would last a lifetime and not fail. But who needs that? I'm not going to live forever. I just want to live till I'm alive, because it's my life, right? Remember that song? It would be nice to have something that will last forever. Materials, chemical, electrical, thermal, and optical properties are determined by their electronic configuration. The valence electrons occupy outer shells, outermost shells that have unfilled. The primary bonding types include covalent, ionic, and metallic. And this is actually what is determining the class of material. The secondary van der Waals bonds are weaker than the primary bonds, and we can calculate the percentage based on the electronegativity of one versus the other. How many of you are looking at this notebook LM generated materials on Canvas? Not so many. How many of you are generating your own? Do you find it at least interesting? I can tell you that, back in the day, these slides, which are provided by Wiley, I made my own slides for mechanics of solids, and it took me the whole semester, and I think they're very good slides. But what Notebook LM is generating is just far more superior based on this. Okay, so you can take so-so slides, if they're provided to you, and you can generate much better content. How many of you have watched the videos? How many of you listen to the podcast? Okay. Is this useful, or am I wasting my time? It's hard for you to say. The reason is because, oh, by the way, have you heard that Google just rolled out Studio? It's a new product. And from my personal perspective, I can tell you that ChatGPT and all those AI, by the way, you can download ChatGPT and have it on your computer. It takes about 9 gigabytes. You can have it not connected to the internet. This large language model. I don't know if you knew that. But if you were to ask me, then during last summer, it was maybe like a 3 to 5 year old. And now it's a very smart teenager. And by this summer, it's going to be, I don't know what. So what I feel is that whatever took me over 30 years to learn, it has instantaneous access, and there's a value in that. For my PhD thesis, I reviewed and read 200 papers, maybe 300 overall, and I wrote 200 pages worth of text, and it took me 5 years to do that. So, the problem of the AI flipping the body 180 degrees or giving you 6 fingers is going to be gone. It's going to get fixed. So the skill set that will be required of you as an engineer will change. We are yet to determine and see how it's going to work out. But I can tell you from my personal experience in the past, there was a lot of redundancy built into the process, meaning that you get hired as an engineer and there's always a supervisor, and supervisor has experience. And by the time they retire, they pass on the knowledge. And there's a lot of things you can learn in the classroom. There's not that much practical knowledge, which you're going to learn on the job, which is going to be job specific, which not one specific class is going to cover. And this is the difference, and it's happening right now. I still can tell a difference when I get a phone call by AI. Hello, and they try to impersonate a person. But I don't know how, I have a feeling. You do not have a feeling that you're talking to AI right now because I'm a live standing person in front of you, right? So the question is, what about the content that's generated by the human versus artificial intelligence? This is the question. And I want to know. So far, it looks like a lot of you are using Chegg and have subscription. Why? I don't know. I guess because historically Chegg was something that provided solutions. You can be looking at solutions all day long without learning much. So I don't know if you learned anything from the stupid LEDs and little car failure. There was a reason I got pulled over, and I'm really happy it happened this way. And if he gave me a ticket, he didn't give me a ticket, he gave me a warning, but if he gave me a ticket, it would be still worth it. Why? Because how else would I know that there's low light in the back? How would you know? So the feedback is very important. How do you know that you're right? There has to be somebody or some system to check, to make sure that you're right. Because we ourselves, you know, there's a saying, your eyes get washed, you don't see your own mistakes. I see you Thursday. Today's Tuesday.